So, today's topic is production and energy consumption calculations. Let us see how do we calculate production in rotor spinning machine. Let rotor speed be Nr in terms of RPM, revolution per minute. The yarn delivery rate, let us say, is V meters per minute. The twist factor English is K, and the yarn count also in English system is Ne. Suppose these are the parameters which are given. Now, we need to calculate the production that a particular rotor unit is producing or generating per unit time. So, unit time we will fix, it could be per hour or per shift, as the case may be. Now, first of all, determination of twist required for a given yarn count and twist factor. Suppose the count of the yarn and the twist factors are given, we need to determine how much twist I have to impart. That we need to calculate first. So, this is what is already probably known to most of you, that twist in terms of turns per inch is twist factor into root over yarn count. This formula is a very classical formula, and this is generally taught when ring spinning is taught. So, twist factor and root over yarn count, these two are related to the twist that we require in a yarn. So, twist factor is represented by small k and yarn count by Ne. So, twist in terms of turns per inch will be k root over Ne, and twist in terms of turns per meter is going to be twist in terms of turns per inch into 100 by 2.54. This will give you the twist in terms of turns per meter. So, k root over Ne into 100 by 2.54. Per inch, if we divide it by 2.54, we get twist in terms of turns per centimeter, and then turns per centimeter, if we multiply by 100, we get twist per meter. That is why 100 is coming on the numerator and 2.54 is coming in the denominator. So, this is how we can calculate the twist that is required in a yarn of a given count and the twist factor stated either in terms of twist per inch or twist per meter, whatever we need. Now, the relationship between machine twist and machine parameters. So, that is what basically gives you how much twist you require in the yarn. Now, the machine we have to set the twist on the machine. So, the relationship between the machine twist and machine parameter. So, twist that is generated by the machine is called machine twist. So, machine twist is the twist imparted by the machine due to rotation of the rotor. Now, this is a new term, that is machine twist, which comes in the case of rotor spinning, but it is not there in the case of ring spinning, because we will also discuss that the twist that we impart on the rotor spinning machines in a yarn, if we try to determine the twist by untwisting the yarn, then we will find there is a mismatch between these two. That is, twist in the yarn and twist imparted by the machines not necessarily are same. The reason is the structure of the yarn. The rotor spun yarn has a differential twist structure. We will discuss about them in coming lecture, some of the lecture, which results in finding out the twist accurately in a rotor spun yarn. Therefore, the term machine twist has come, that is the twist that is imparted by the machine due to rotation of the rotor. Now, when it comes to the machine, the twist that the machine is going to generate in turns per meter is the rotor speed in revolution per minute divided by the yarn delivery rate in meters per minute. So, RPM stands for revolution per minute and yarn delivery rate is also meters per minute. So, if we this ratio is the twist that is generated by the machine. So, this is N R by V, or N R, R stands for the rotor. So, rotational speed divided by the delivery rate. Now, yarn delivery rate V therefore becomes small n r by twist in terms of turns per meter. So, now what comes is that turns per meter, the twist is related to the twist if we express in terms of turns per inch, or if we want to express in terms of twist factor. We have already seen earlier that twist per meter is actually, if we go back to the previous slide, it is written there, we are basically substituting this value. This is what it is, that is this twist turns is k root over n e by into 100 by 2.54. So, this value actually we are trying to substitute. So, if we go back to the slide that we are looking at, so we have just replaced this. If you do that, we get this. This is the equation number 4, that is yarn delivery rate V becomes rotor speed and twist factor, and this is yarn count in NE. So, therefore, production by a rotor, by a single rotor, will be yarn delivery rate, which could be meters per hour. If they want the production to be per hour basis, then delivery has to be calculated how much yarn is delivered per hour. That multiplied by the yarn count if it is given in text, which will give you the amount of the weight of the yarn. If we want to calculate in terms of kg, then you have to divide this by 1000 into 1000, because yarn count text, if we go by the definition of text, it is gram per 1000 meter. Therefore, yarn delivery per hour has to be converted into how many 1000 meters it is. So, therefore, we divide it by the 1000. First 1000 is giving in terms of kilometer of yarn, you can say, because total yarn delivered divided by 1000 will give you how much yarn is delivered in terms of kilometer. And then that if it is multiplied by yarn count given in text, it will give you the weight of yarn in gram. Now, gram is then has to be converted into kg. Therefore, another 1000 will be coming, divided by another 1000. That means, the denominator becomes 10 to the power 6. That will give you the production in terms of kg per hour. So, here we are writing the yarn count in terms of text, because that makes the calculation easy. And then if we want it to be written in terms of any, that also can be done, because we need to know the conversion formula between any and text. So, the easy way out is that you first consider the yarn count in text, do the calculation, it will be faster, it will be easier. Otherwise, one can also do the calculation using any value of the yarn. So, if we do that, suppose we want to find out the production, same production, instead of text we want to know it in terms of any, then what we are doing, we are changing the text into any, and the relationship between these two is text value is always 590.5 divided by the count of yarn expressed in any. So, this is what we are placing here. Everything remains same as it was shown in the previous slide. And then we simplify this and we get 60 into V. 60 is coming because per hour. V is given in terms of generally meters per minute. So, if I want to calculate per hour, because the time unit is hour, therefore, we multiply it by 60. So, it is 60 V into 590.5 by any into 10 to the power 6. That gives you the production in terms of kg per hour if the yarn count is expressed in terms of any. Most of the time in the Indian textile industry, the counts are expressed generally in any. Therefore, we need to know the formula when the count is expressed in terms of any. Now, substituting the value of V. So, equation 5 also is a formula to calculate production. Now, if I want to replace V by rotor speed, then we can get another formula to calculate the value of the production. That is, what we are doing here, substituting V from equation 4. So, in the equation 4, the value of V was stated, that is what we are bringing it here now. So, it is this part is actually V, where NR by K, this should not be N C, this is NE into 2.54 by 100 into 590.5 divided by NE into 10 to the power 6. So, this whole this is what is basically EV. Now, let us look at equation 4 again. Let us go back and see what is equation 4. This V is here. So, this V is stated NR by K into root over NE 2.54 by 100. So, same V we are basically substituting here. So, this is basically V, and if we simplify it, we end up with this formula. And if we, these are all constant, and this value will be 0.0009, and the other parameters are NR, that is the speed of the rotor, K is the twist factor, and NE is the yarn count in English system. So, equation 6 also gives you production in terms of kg per hour. So, either 5 or 6, anyone can be used depending upon which are the parameters which are given. So, equation 6 gives you production figure in terms of rotor speed twist factor and yarn count. These are the three unknown parameters in these equations, these three. So, therefore, we can say that the production rate is proportionally to what? Is proportional to V and inversely proportional to the yarn count expressed in NE, or it is proportional to NR rotor speed divided by twist into NE, that is inversely proportional to twist and inversely proportional to the English count. So, you can say this is one when the count is expressed in English system. If we want to express the count in text system, in that case the production figure will be proportional to V, directly proportional, and also directly proportional to the yarn count expressed in text. Or if I replace V by the rotor speed and twist, because V, rotor speed and twist are interconnected there. Twist is a function of rotor speed divided by delivery. So, they are all connected together. So, V can be replaced by NR by T, and therefore, we can write V is proportional to either NR rotor speed or proportional to count of the yarn expressed in text system and inversely proportional to twist. So, we can generally say production therefore, mainly depends upon the rotor speed. More the rotor speed, we can expect more will be the production. It will also depend upon the yarn count, but whether it will be dependent on it inversely proportional to the count or directly proportional to the count, all depends upon the counting system in which we express the yarn count, and it also depends upon the twist. So, if we increase twist keeping other thing constant, what will happen to the production? Production should increase or decrease? Production should decrease. It is very obvious, because T is in the denominator, and if we increase the rotor speed keeping other parameter constant, the production should increase immediately. So, if we want to increase production rate, you have to go for higher speed of the rotor, or you have to decrease the twist in the yarn. You have two options: either you increase the rotor speed or you decrease the amount of twist that you require to spin the yarn. The other thing is the course of the yarn, the model with the productions. So, if it is in text system, then it is directly proportional, and in the case of indirect systems of yarn counting, it will be inversely proportional. But generally we can say that when other things remain constant, the coarser the yarn, more will be the production. So, these are the three important parameters: rotor speed, yarn count and twist. These parameters affect the production rate. The rotor speed generally can be changed to increase production, but there are certain other problems that we face when you try to increase production by increasing rotor speed. That is, what can happen if we try to increase production by raising rotor speed? What could be the negative consequences of this? What? Yarn breakage, correct. It could be yarn breakage, because the tension is going to increase simultaneously. So, generally rotor speeds are optimized first, and that optimization is done keeping in mind the tolerable level of end breakage. If the end breakage frequency goes very high, then will not, that means the efficiency of the machine will go down, and therefore, the whole operation becomes very commercially not successful. So, there is a tolerable limit of the end breakage rate in rotor spinning machine, as this is also true for ring spinning machine, for that matter any spinning machines. And the most sensitive parameter that affects end breakage rate is the speed of the rotor in this case. So, therefore, once the rotor speed is optimized for a given type of fiber and for a given type of count of the yarn, then we do not change the speed much. We try to then change other parameters. Count is also a parameter that cannot be changed at will, because you have to produce a yarn of a certain count only. We cannot say I want to change production, therefore, I want to make the count coarser or make it finer to reduce production. That is not acceptable, because count is decided by some other requirement. So, that cannot be touched. So, only the two parameters that can play a role is rotor speed and twist. While rotor speed, as I said, is not really always, may not lead to a higher production rate, because it can increase your end breakage rate and thereby can reduce the efficiency. The twist is other parameter. Okay, the twist, if we reduce, the production is going to increase. But what is the negative fallout of increasing or decreasing twist?
Twist will less, again yarn breakages will be more, because gripping will be not that much good. And
if the twist is less, then what will happen? The strength of the yarn may go down, and that can also lead to breakage. There could be other thing also if we reduce twist, that is the flow of torque in the band of fiber which is pressed against the rotor wall, that also can get interrupted. If there is not sufficient torque available in the yarn arm within the rotor, then also the twist cannot flow into the band of fibers which are pressed against the rotor wall, then also it can lead to breakage. So, therefore, too much reduction of twist may lead to breakage due to two different reasons. One is because of the yarn is becoming weak, and the other one is you may not have sufficient torque available in the yarn arm, and therefore, the fibers may not get twisted properly, especially a bundle of fibers which are pressed against the rotor wall. As we have, I think we have already discussed in the previous lecture. So, these are the the phenomena which we should keep in mind, and accordingly we should try to increase or decrease production. So, a lot of other effects could be there. The other effects could also, which I have not discussed, is that the rate of injection of dust particles in the rotor. The moment we try to increase production rate, especially with cotton, that means my sliver feed rate is going to increase simultaneously. So, per unit time I will be feeding more dust in the rotor, and these dust are going to accumulate. Some of the dust may escape or may be taken out by the yarn itself, but some dust particles also will be accumulating within the rotor groove. And we all have also, I think I have discussed earlier, that as dust particle keeps accumulating within the groove, a time comes when the thickness of the dust layer is such that it leads to breakage of the yarn. The fibers cannot get packed tightly now, because the corner of those groove is already loaded with lot of dust particles. So, higher production rate means more dust will also enter, and therefore, frequent breakages can also happen. So, these things we have to keep in mind. Now, we will take an simple examples to solve some problems. They are very straightforward simple problems. Calculate production from the following data. So, what data are given? One is the count of yarn, which is 25 NE. The rotor speed given is 45,000 RPM. The twist factor in English is 4.5. So, from these three data, you are supposed to calculate the production rate of the machine, not the machine probably per rotor. If we can calculate the production per rotor, we can also calculate the production for the entire machine. For that, we need to know how many rotors are there in the machine. Generally, the number of rotors are close to 200. The solution is we are using directly the formula that I have shown you earlier. So, this is the formula. Sometimes remembering the formula is difficult. So, if you do not remember the formula, how to solve it, that also we should know. Then you should go by the simple logic that how much yarn I am producing per unit time. Here the production is to be calculated per hour. So, the unit is per hour. So, you can find out also that how much yarn I deliver or I produce per hour and what is the weight of that yarn. This is what you require to know. What length of yarn I am producing, and now if I know the count of the yarn, what is the weight of that yarn? That will give you production. Only assumption is that the efficiency is 100%. There is no breakage. So, that is the assumption. Sometimes some efficiency figure may be given also. Now, here in this case we are directly using the formula that we have developed, and in that formula the parameters are 3: speed of the rotor, the twist factor and the count of yarn. So, these three are given in the example. We simply substitute. If we substitute, we get this figure 0.072 kg per hour. If it is to be shown in terms of gram per hour, we have to multiply it by 1000. That will give you gram per hour. So, in that calculation, the efficiency figure has not come. That means, we are not considering the efficiency part, or we can say that efficiency is 100%. In that case, so much of kg of yarn will be produced if it is producing 25 NE yarn. Now, one more example. A rotor spinning machine is spinning 16 NE yarn, 16. The rotor diameter is 56 mm. The rotor speed and twist multipliers are 70,000 RPM and 4.4 respectively. This is what is given. Calculate the production per rotor per hour in gram if the efficiency is 95%. So, here the efficiency figure is given. That means, 5% of the time the rotor did not work, did not produce. 95% of the time the rotor was running. So, if I say in an hour how many minutes the rotor did not run, what will be the value? In 1 hour how many minutes the rotor did not produce any yarn. What will be that figure? Take some time and calculate per hour how many minutes the rotor was idle. Though that question has not been given in this example, but that is an additional simple question we can put. So, ideal time is 5%, that means 5 by 100 into in 1 hour is 60 minutes. So, ideal time, if we want to find it out, it will be how much? $60 into 5%, 5 by 100. That means it is basically 3 minutes. 3 minutes the rotor did not work, it was idle. 57 minutes it has worked. And if we want now to calculate the production, again first of all we calculate production with 100% efficiency. Again we are using the previous formula, directly putting these values, and we get a figure 0.22 kg per hour. This will be close to this, and with 95% efficiency, simply multiply it by 0.95 or 95 by 100. This will give you 0.209 kg per hour. If we want gram per hour, we multiply it by 1000. It will be 209 gram per hour. This will be approximately, these are the figures. The figures might little change depending upon how many decimal points you have considered in the calculations. So, yes, there is no need of rotor diameter. This has been given so that you get confused. So, no use of rotor diameter in this particular example. So, this kind of the problems are quite simple in nature. So, now difficulty is not there in calculation part. Another example, example number 3. A rotor spinning machine is producing 9 NE yarn at 45,000 rpm. The twist multiplier rotor diameters are 4.5 and 40 mm respectively. Calculate the delivery rate. Calculate the delivery rate. So, the steps are already shown. Now, sometimes we may need to know what is the delivery rate. So, delivery rate, twist and rotor speed are interrelated as shown in this. Twist is Nr by V, where V is the delivery rate. So, this is what we have to make use of this formula. So, N delivery rate V will be Nr by twist, and twist in terms of meter, because if we know delivery rate in meters per minute, then I have to know the twist also in terms of turns per meter. So, many times people generally forget, and they put the figure of twist in terms of turns per inch, and they make a mistake. If the delivery rate we try to find out in meters per minute, the twist also has to be in the same unit, that is turns per meter, not turns per inch. And we need to know the relationship. So, this entire formula has to be used, that is the deduction of this already has been shown earlier. So, one can go step by step. instead of using the last formula. If you can't remember the formula, then you go step by step, that is, you first find out the twist in terms of twist per inch. If we know the twist factor and the count, then twist per inch you convert into twist per centimeter and twist per meter, and then use that. So, not necessarily that you have to remember the final formula always, but you should know the logical steps that you have to follow in order to solve a simple problem. Here we are using the formula directly, and therefore, it becomes just a matter of substitutions. So, all the figures are given, the parameters are given, we are putting those values and getting a value 84.6 meters per minute. So, in this case we expect the delivery rate to be 84.6 meters per minute. So, different types of example could be there. Sometimes you calculate the production rate, sometimes the delivery rate, sometimes you may be asked to calculate the efficiency figures, sometimes the stoppage data may be given and you have to calculate the production. So, various ways the problem may come, but the solution is not difficult, only thing that you have to be logical in your approach, you will be able to solve the problems. Next one is the energy consumptions or power consumptions. Rotors are made to run at very high speed. So, we all know the higher the speed, more will be the energy consumption, that is electrical energy. So, there is a formula, is empirical formula which has been developed by Searle Institute UK long ago, and this formula states that the power consumption in terms of watt is 3.5 into 10 to the power minus 12 into n r to the power 2.5 and d r to the power 3.8. This is an empirical equation based on, basically empirical equation means that it is based on data. By collecting large number of data, these values, such kind of regression equations can be found out. So, if this is the formula which is given, then using this formula we can find out the energy consumption, at least some idea we will get how much energy is consumed when we run a rotor at a certain speed. So, in this formula there are two parameters, one is Nr which is rotor speed in RPM, and the other one is Dr, diameter of the rotor in inch. You have to remember the unit. The unit has been given in terms of inch. It is not that we will not be able to change it to centimeter or millimeter, we can do that also. So, inch can be easily converted to millimeter, and then the formula therefore, will be get little modified, the constant term will then change if I want dr to be changed to suppose millimeter. But the formula as suggested by the Searle Institute is given here. So, this formula can be used directly to calculate the power consumption. Like an example is given here, from the following data calculate power consumptions per rotor. Rotor diameter is 38 mm, a typical rotor diameter could be 38, could be 50, could be 65, and rotor speed is 60,000 rpm. Rotor speed can go up to 1 lakh rpm nowadays, it can go to 1,10,000 rpm also, and the rotor diameter can go on the lower side to 28 mm, the minimum diameter. So, that is the range, that the diameter can vary from 28 mm to almost 65 mm, and the rotor speed can vary from 45 to 1,20,000 rpm, depending upon the type of yarn we want to produce. Now, for this, if we want to find out what is the power consumption, so we make use of that previous formula that was given in the previous slide. This formula we make use of it. So, values are given and you substitute them. Such calculation would need obviously the help of a calculator. If I do this, if I just go by substitution, and then we will get a figure like this, and the last figure which is coming here is 14.4 watt. That is, to run the rotor, it is consuming 14.4 watt of electricity, electrical energy, one single rotor. So, we are simply using this formula, and the point is, what is to be noted here, that the power consumption increases disproportionately at the power of 2 to the power 2.5, between 2 to 3 actually it is somewhere lies. So, with this increase in speed, the power consumption goes very, very high. With increase in speed rotor, the production rate will increase linearly. Suppose if I express the count becomes coarser, the production rate will increase linearly. Or if I increase the rotor speed, then the production rate will increase linearly. This P stands for not production, but for power. And the power, rotor speed to the power 2.5. So, with increasing rotor speed, the power consumption will go very, very high. So, per kg the production rate of the per kg the power consumption is going to increase, and it can also increase at a very faster rate with the increase in rotor diameter. So, if you are going to increase rotor speed in order to increase productivity, then we can decrease the rotor diameter simultaneously to keep the power consumption maybe at a constant level. Because if I increase NR and decrease DR, we may find a place where probably the power consumption may not change much. Otherwise, if the rotor diameter remain fixed with the increasing rotor speed, the power consumption will be very, very high. Or if we just keep increasing the rotor diameter, keeping the rotor speed same, then also the power consumption is going to increase at a very faster rate, because it is almost diameter to the power 3.8, a very high figure. That means, the power consumption in the rotor spinning is very, very sensitive to these two important, one important you can say factor. One is related to the machine factor, that is diameter of the rotor, and the other is related to the process factor or process parameter, that is the speed of the rotor. So, one is machine parameter, the other one is process parameter. Both of them are very, very sensitive as far as the power consumption is concerned. With this, we close this session of production calculation and some energy related also calculations. So, what we see here, the basic methodology that we follow to calculate production actually remains same for all types of machines. Ultimately, what we need to know how much we are delivering in terms of length per unit time, and then convert it into how much kg per unit time. Whether it is a draw frame producing sliver or roving frame producing roving, or ring spinning machine producing yarn, or rotor spinning machines or other spinning machine that we will see. So, the basic methodology is all same, it does not change. Okay, with this we close this session. Thank you.